name is Gabe. My friend over here to my left is Arbri. And then our two other group team members who are going to be joining us for the Q&A session are Kevin and Jerry. Today we're going to be talking about road safety in Toronto. So, as with every other team here, we were given access to the Toronto open data sets, and we were given the task that with the resources provided to come up with an issue that affects as many people as possible, and at the same time is quite simple to solve so that it can be solved in a reasonable manner without costing the city too much money. Now, we used big data science. We applied a bunch of new technologies that we found, for example, Statistica, and we ran it through and found some interesting results.
And so the general premise there was that Toronto's a major urban center. Driving is almost requisite at this point, and there's a lot of moving about large distances. So based on that concept, we decided to look into traffic.
So traffic, road safety, it seems like a relatively mundane issue, but in reality, in 2013 alone, more people died from complete accidents in the city, from traffic accidents, than actually premeditated homicide. So that's actually pretty crazy to think about once you take a look into it. And then even further than that, with about 50,000 avoidable collisions every single year, there's a lot of room for improvement, and I feel like this is something that the city of Toronto should definitely be focusing more on. So that considered, our group got together and we thought of a hypothesis. So our initial hypothesis was, after thinking some time, well, maybe if there are more cars on the road, a higher concentration of cars and volume, then there's probably a greater chance to be hit by another car.
Yeah, basic probabilities in that sense. For this presentation, we use a lot of specific terms that we use internally, so I'll define them here. Commonly, commercial zone, a neighborhood where the number of locally employed outweighs the number of residents. Residential zone, the inverse of that, a neighborhood where the number of residents outweigh the number of locally employed people. A traffic collision, based on the data that we grabbed, they divided up collisions for vehicle to vehicle, accruing damage of more than $1,000 or where personal injury occurs, and collisions that were involving a vehicle and a pedestrian, a cyclist, etc. They did not make the exact distinction between each point of the data, but that there are different sets for collisions that include only car to car and collisions that include a vehicle and some other entity. Road volume is an elemental principle for this presentation, essentially the number of cars that drive through a neighborhood over an interval of 24 hours. And the collision to road volume ratio, this is something that we elucidate on later on in the presentation, but was elemental to the way that we picked what to research and why we thought certain things were, basically why we thought certain areas were more extreme than others were less extreme, is essentially the ratio of the number of collisions divided by the road volume of a given neighborhood.
So I believe we were actually the only team to use Statistica, and I'm kind of surprised because it was an extremely easy to use program. It provided us with a lot of support. So as opposed to having to create a formatted text document in the case of Python, or having to create a master graph for everything, or rather a master table for all the information, all we had to do was import a couple of Excel documents and then merge them using nodes. So as opposed to maybe the 20 minutes that it would take to create a master table and format it properly in a text document, it took us about 5 minutes to merge them with nodes. In addition to that, we also, as soon as we had these nodes into a master table, all we had to do was select the data that we wanted by dragging over it and then creating our own graphs, which was very, very interesting, and it was a useful way to go about the actual project. So as for the actual data sets we used a bunch, but for a couple that we went more in depth with after considering relevance, we used the demographics data set, we used economics data set by different neighborhoods, and then we also used the transportation open data set. So next we're going to be looking at, after considering relevance and what is actually useful in our data, which we will go over in a little bit, we had to determine what an outlier was to our data. So to us, we decided that an outlier was an object which had an abnormally high collision to road volume ratio. So what is a collision to road volume ratio? We talked about it a little bit in our definitions, but essentially it's exactly what it is. It's a ratio between road volume and collisions, and using this, we were able to rank each neighborhood. Then what we did is that we used graphs that we developed using different x and y's, that we use different blah 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 to I'm a little bit tongue-tied. So after that, we used a little bit of observation as well. So for example, if a group of outliers were very close together, we could consider it something as, oh, well, they're near to each other. Perhaps it's not as an extreme of an outlier because of the way that the neighborhoods are listed from left to right. Perhaps it's something in the area. So rather what we aim to do is we aim to look at areas with extreme isolation from their other neighbors while having an extremely abnormal ratio dependent to the trend line. At the end of the day, we determined 6 different total outliers, 3 of which were above the trend line and 3 of which were below the trend line. Why we chose 6 was because 6 was low enough to be manageable in our time frame, but at the same time was also meaningful to the total impact of the data.
We name these outliers positive and negative. This is not necessarily related to the numeric value, but the way we define it is that positive means the ratio is low, and generally they are safer. So positive in a very pathos sense, not logos. And the same thing with negative. It means the ratio is very high and it could be considered more dangerous. So as we said before, we took this ratio and we plotted it, and we put it in both a chart form and graph form, and we used the graphical element of it to pick things that were isolated and also extreme for their place in the domain. And the same thing for the actual, for the chart plot, we picked things that were significantly extreme from the average, as well as significantly extreme from their own neighbors. So this itself is the plot. In circled in red are what we chose as the negative outliers. All these numbers are neighborhood IDs, as all the data sets include the same neighborhood IDs that are based on geographical placement of the neighborhoods. And you can see 1, 31, and 26, they're very far out from everything near it, and also isolated from each other. And the same thing with 49, 108, and 115. This itself is the charted plot of it. The average ratio that we found was 0.081 of collision to road volume. And for downstream road, the first one there was a ratio of 0.319, so 3.2 is a pretty significant increase, whereas the lowest one that we have, 0.0091, is significantly lower than what we had as the average.
So I also want to point out something very interesting. Because we had the unique opportunity to look at all the other presentations before ours, we made an interesting note that ID number 1 seems to come up a lot, which is very interesting. So let's go to the next
As
one.
an interesting fact, odd observation. So yeah, we looked at this is what we looked at to validate our data. We looked at the area size of local population, road kilometerage.
Yeah, I'll go on this. So now we're actually going to be going on how we validated our data. How did we determine what was relevant and not? So we looked at different things like area size, size of local population, road kilometers, and road volume. Why? Mostly tying back into that original hypothesis of, well, if there are more roads in a neighborhood and if there are more mileage of roads, then there's probably going to be more cars on those roads, and therefore there's going to be a higher density of people on those roads. We also looked at, of course, the total number of collisions, because that's, again, very elemental to our hypothesis. Next is what I consider one of the most interesting parts of what we found. So what did we determine was not relevant to our data? So looking at our factors over here, we have things like age groups and gender and ethnicity. So basically, does the makeup of a neighborhood based on gender or age group or ethnicity contribute to the safety of driving on those roads? And actually what we found is, most of the time, no, they really don't. So for example, age. If you go into a neighborhood with a lot of old people, go back to focus. So if we go back to a place with a high demographic of old-aged people, whereas usually in your mind you think, oh, they're older, they're probably less alert on the road, and therefore higher chance of getting hit. Actually, no. We found that places with a higher density of elderly people had a lower chance of being hit in those areas. Same thing goes for gender. Actually, in Toronto, most neighborhoods have a majority female population, so you can't really derive anything significant from that. one of the most interesting things out of this is the culture and ethnicity. So no, if you're from an immigrant population or you're a minority, that's not going to affect how safe the roads are to drive, including